Hi there, welcome. I'm Flora, and today I'm going to be talking about mapping the impact of flooding on subsequent flood risk for the River Tweed and investigating changes in the discharge inundation extent relationship. So the key research questions and aims for this project. The first research question is, how does severe flooding morphologically change the River Tweed? And to answer this, the changes in riverbed elevation and the areas of deposition and erosion will be mapped to see the effect of flooding on the morphology of the river. The second research question is, what is the impact of morphological change on subsequent floods? And to answer this, hydraulic flow models based on river channel morphology for pre and post flooding will be used to predict the inundation extent and inundation depth. From these results, probabilistic maps will be produced. The third research question is, do tipping points exist in the flow-inundation relationship, and do they change? So to answer this, the relationship between the input discharge and the output inundation extent and depth would be investigated, and to see if thresholds exist between the discharge and the extent. So these research questions were heavily influenced by several papers by Collette, Feynman and Beavers, which will explain how changes in the peak flow of rivers can lead the river to morphologically respond. And this response of erosion and or deposition, which changes the river topography, can change the conveyance capacity of the river and therefore the flood risk. This has been shown to be more influential on the inundation extent of the flood than changes in the river discharge by a paper by Guan in 2016. So topographic controls were shown by Beavers to create tipping points in the inundation flow relationship, which could be investigated further using a probabilistic approach, which will be done in this project. In 2014, Bevan identified that there were several sources of uncertainty in flood modelling, three of which were floodplain topography and cross-sections, catchment change and climate change. In 2017, it was made evident that these sources of uncertainty in flood modelling should be identified and communicated to allow for better decision making and flood management. So there's a lot of motivation behind reducing these uncertainties and their influence on flood modelling. This is because we are constantly attempting to assess and predict flood risk due to the fact that flooding is so widespread and destructive. These tipping points noted by Beavers would be extremely useful for planning and policy change. This is because flood risk is mostly dependent on the inundation depth, which has been shown to be impacted by the morphological river changes during extreme flooding. This figure on the right shows the output maps from a study by Collette in 2018, which identified 134 catchments which were considered hydro-hazard hotspots. And these hotspots are areas where there's expected to be a lot of change in the flood and drought characteristics in the future. And it can be seen that Berwick-upon-Tweed on the River Tweed, just by the Anglo-Scottish border, has been identified as a hydro-hazard hotspot. So this hydro-hazard hotspot of Berwick-upon-Tweed was selected as the study area for several reasons. Firstly, the River Tweed, which is a gravel bed river, experienced peak flows during the 2016 floods, and most of the postcodes in the region are at high risk, with some considered medium risk. Also, towards the coast, as the river nears the coast, there are high levels of deposition, which could be linked to changes in conveyance capacity and therefore flood risk. But this region was also of particular interest because the 5 kilometre reach near the coast has high resolution 1 metre LiDAR data for 2015 and 2017, which is unusual to find such high resolution LiDAR data so close together. This was actually a limitation at the beginning of the project because it was hard to find data which was close enough in time so that the impact of a flood could be investigated, because some LiDAR data that it only repeat the same coverage of the area every 10 years or so. And there was also the presence of daily flow gauge data, which also made the area of particular interest. So to answer the research questions, the following methodology will be used. Firstly, high resolution LiDAR data, as mentioned earlier, about 1 meter resolution, will be used for pre and post flooding, so 2015 and 2017, to estimate the morphological change of the river channel. From this data, steady state 1D hydraulic models will be used, inputting river channel geometry and boundary conditions before and after the floods. The river discharge from the 2016 floods would be then input to both hydraulic models to have a predicted inundation extent and depth. And then predicted peak flows would also be input into both the hydraulic models and probabilistic maps of flood risk produced for both. And then these results can be investigated to see the threshold and the change in flood risk. So on the left, you can see a picture of LiDAR data, which is light detection and ranging data, and it was chosen because it can produce high resolution elevation data of the ground. And then the picture on the right shows a cross-section of river cross-sections which are used to produce a 1D representation of the river flow in hydraulic models. So these figures show how 1 meter resolution LiDAR tiles of digital surface models of the river for 2015 and 2017 have been downloaded into QGIS, and then these two digital elevation models have been used to create a DOD, or difference of elevation model, between the years. And this DOD on the right is used to see the change in elevation of river topography between the years. So this graph shows a cross-section of the river, and the purple line in the graph shows the DOD, so it shows the differences in elevation, which highlight areas of deposition or erosion. So this will be used to estimate the net sediment budget of the river, and whether the flood conditions were flood cleaning or flood depositing, which is essentially whether the river was eroded or more deposition occurred. So the next stage moving forward with the project will be to build hydraulic models using HECRAS, which is a simple steady state 1D flow model. This was chosen as the method because hydrodynamic models are particularly useful because they can be manipulated and the input can be changed to investigate the impact. So this 1D model was chosen because a 2D model has been shown to be unnecessary and the simple 1D flow model can be assumed. The input data for the hydraulic models is flow data and river geometry, such as the river cross sections, Manning's roughness coefficients, and different boundary conditions. So the output of these models will hopefully be used to map the area of the floodplain expected to be covered during the flood and depth under 2016 flows. So the discharge from the 2016 floods will be input into both hydraulic models and then the results compared. And after this, the future flows hydrology database will be used to input predicted peak flows for the future, and these will produce inundation rasters for each flow, which can be used to produce probabilistic inundation depth maps, an example of which can be seen on the right from a study in 2013, and hopefully similar maps will be produced for the River Tweed. And from here, the thresholds and the impact of morphological change can be properly analysed. And these are just some of the papers. Thank you very much for listening, and hopefully there are some questions.